So now let's see how the energy transfer takes place in a centrifugal pump. So you have a centrifugal pump here, and you have, let's say, a reservoir where you take in the water, and then you deliver it at a higher tank. That's what happens at your in your house, right? Okay, so this is the center line of the pump. Let's say from here the height of the water in the tank delivered is say HD, and this height is suction. So this is, let's say, the groundwater or something. The ground level is HS, and this is HT. This is your centrifugal pump impeller. Or okay, so now if I happen to write energy balance equation between here and here. Okay, so so first is between 1 and the delivery point and the suction point. Well, from here, if I take this as the reference, the pressure is atmospheric, PA by rho g. Okay, and this is the velocity is 0 because it's a very large reservoir, so velocity is 0. So the head term, this is a reference, so I don't have a head term. Then at 2, the pressure is again atmospheric, let's say it's open to the tank, plus the velocity, again a very large source, so no velocity. From the reference level, this is the reference level, the height is HD plus HS. Okay, okay, so this was the input energy, inlet energy of the fluid. This is the outlet energy, plus you're supplying some work by the pump head done by the pump. So this is the input energy of the fluid plus head delivered by the pump. Okay, and you will have some losses here and here, so all that you have to subtract. So that's when you subtract, it goes to the right side. So this is the head loss in the pipe and loss in the pipe as well as in the pump. Okay, so if I cancel all that, so what I get is head supplied with the pump. If I cancel the pressure, is the difference in the height, or the height change from the lower reservoir to the reservoir, plus the head losses, the pump and the pipes, suction and the delivery pipe. So this is the height from where you're lifting the water from the reference to the outwards. So this head plus the losses, all that is what is the pump supplies. So that is one thing. Okay, so all this can be expressed in a bar chart kind of form. Like if you have a shaft, let's say the shaft is connected to the impeller and the shaft is supplying power P. Now shaft might be connected, so this is your shaft output. Okay, the shaft is connected, and I mean shaft is connected to the impeller, but in between you may have some mechanical losses because of the friction at the bearing and stuff like that. So that is all is mechanical losses. And what we get to the impeller is, let's say this is 1 what we get at the impeller is the power minus this mechanical losses. Now the output of the impeller, let's say this is what we are tracking output. Shaft output is P. Okay, we are tracking outputs only, and the impeller output is basically your the head delivered. Okay, the head delivered, that is H, which is your VW. I'm just writing the tangential component by G. So this is the head delivered by the pump. Okay, and now there might be some losses, hydraulic losses in the pump. So the head that is going out of the pump, I'm just writing manometric head. It is called manometric head. And then you have the friction losses in the suction and delivery, friction losses in the pipe. And what you get at the outlet is just the change, that is HD plus HS, right? Delivery plus suction head. So there are a couple of things. First, the shaft power, okay, and then you have the mechanical losses. Okay, So what you get is this head, which is rho Q into H, that is delivered, which is rho Q VWU by G. This is the head that is delivered by the impeller. Now you have some losses in the pump and what in the casing and other friction losses in the pump. So what you get at the outlet is the manometric head. We call that manometric head, which is less than this rho Q VWU by G at the outlet of at the exit of the pump. And then you have the friction losses in the pipes, all that FLV square by 2 GD for the suction and the delivery pipe, friction losses in suction and delivery pipes. And what you get at the outlet is your static head, is your change in the height, rho Q into change in the height. So this is static head. So if I don't have any losses, this power should be just equal to the static head. Okay, so that is how you find. So the total efficiency of the pump is, so this part is the mechanical efficiency where you are delivering this. Okay, so let's write down in steps. So mechanical efficiency is how much you're delivering to the pump, is rho Q WU by G, that is the head delivered to the impeller by the shaft power. So this is mechanical efficiency. Then your hydraulic efficiency is how much better you convert this into the head at the exit of the pump. So that is rho Q, the manometric head, by rho Q, the power input to the impeller. That is hydraulic efficiency. And then basically your the hydraulic losses in the friction, hydraulic efficiency outside, hydraulic efficiency. So this is hydraulic efficiency in the pump, this is hydraulic efficiency in the pipe. So that is the static head by your rho Q manometric. So most of the time we don't segregate this, but I have just explained. So the final efficiency, the overall efficiency is the static head, the power associated with the static head is rho Q static head by the shaft power. Okay, so this is all about summary of about what are the losses, typical losses, where it can happen and stuff like that. Now let's have a word about what is pump cavitation and stuff like that. So you already seen that what is cavitation briefly, but let's now go into detail. So I'll just draw the same diagram which I have drawn before. You have a reservoir from where it has to lift, the pump has to lift water and deliver at the outlet somewhere here. Okay, so this is where your atmospheric pressure is there, and this is situated below the pump axis, that is suction. And so now I'll write between 1 and 2, that is I'm applying energy equation between the reservoir level and the pump input or the pump inlet. So at the reservoir it's PA by rho G, there's no velocity, that is the reference level. Okay, so this plus this is the energy content of the fluid at the reservoir, plus now there might be some head loss. Okay, so that just we are neglecting it. Okay, so that is the energy at, so what is the energy at the outlet? At the outlet you at 2 you have P2 by rho G plus velocity, some velocity at the inlet, so V2, and the height is HS, plus if you have some head loss in the suction, that you have to write. So now this P2 by rho G, obviously from this we can say that P2 will be less than the atmospheric pressure and it shouldn't go below atmospheric pressure, it shouldn't go below. So basically the input or the inlet pressure of the fluid From this equation we can say the inlet pressure of the fluid is less than the atmospheric pressure. Okay, because all these terms are non-zero positive terms, less than the atmospheric pressure, but it shouldn't go below the saturation pressure at the operating temperature. Otherwise there is a chance of converting into vapor or vapor formation. So this can be understood from your TS diagram for a fluid. So general diagram is something like this. Okay, so now you are here, let's say you are here. Okay, so let's say, I mean, this is the atmospheric pressure and your temperature is 25, so you are here at 25 degrees Celsius, atmospheric pressure of 100 kPa, you are here. But if you go, and this is 100 kPa, constant pressure lines are like this, and let's say this is, I mean, at 25, if you look at the saturation pressure in the steam tables, that is 3.98 kPa. So at 25 degrees Celsius and 100 kPa the fluid is here. But now if you reduce the pressure at the same temperature, okay, let's say you move along this line, this pressure, is this pressure at which it starts converting from liquid to vapor. So it will basically convert at this pressure 3.98 kPa, where some liquid will convert into vapor. So that's the reason why you shouldn't go below the saturation pressure, because there will be a chance of vapor formation, and once vapors form, then it is, so that's the thing, it is possible for the local pressure inside the pump to fall below vapor pressure. Okay, so vapor pressure means, I mean, the saturation pressure. So if your pressure is less than, if pressure goes below the saturation pressure, your vapor filled bubbles called cavitation bubbles appear. So in other words, the liquid boils locally. I can say there's a local boiling of the liquid which leads to this vapor formation, and this happens only on the suction side of the impeller. For a centrifugal pump, there's a chance of cavitation only on the suction side, because the pressure, because of this reason. That's what the suction side, if you, from the reservoir to the suction, if you write equation, you will get to know this, because then the head is applied and the pressure is increased from the suction to the delivery. So delivery, there's no, always the pressure is above atmospheric pressure. Okay, so after these cavitation bubbles form, they transport to the regions where pressure is higher, and then because the pressure is higher, these vapors collide, they collapse, and so always there's a this is undesirable because it causes noise. The collapse, because the collapsing, the vapors collapse as they move to higher regions. They collapse, but then they collapse with noise, and it leads to vibration of the structure, and most importantly, the most important thing is they damage the blade surface. The blade surface is damaged, so it, over the period of time, it just erodes. So the basic objective is to avoid cavitation. We need to ensure that your pressure shouldn't go below the saturation pressure. So for what do the manufacturers of the pump, they do is they have one term called NPSH, that is net positive suction head. Net positive suction head. So what they do is they measure this P by rho g plus V square by 2g, this entire term. Okay, how much higher is this compared to your the suction or the Psat by rho g. So they compare this with the suction head, and if NPSH, so this So NPSH, and they express. So let's say if I'm a manufacturer, I'll just design that my actual pressure by rho g plus v square by 2g, this difference compared to your suction head, it has to be say 5 times. So this NPS, that will be your requirement. So always when you operate, your NPSH should be greater than your NPS requirement. So this is just a design parameter to ensure that always your operating pressures are well above your, though they are below atmospheric pressure, but they are well above your saturation pressure. Now let's come to an important topic called pump scaling laws. Okay, well, pump, you have a lot of parameters which can affect the head. Let's say the head, what are the factors on which the head may depend? The head may depend on the volume flow rate, your discharge, your surface roughness, your speed, your density, so all this, when the physics is complicated and when one of the output parameter depends on a lot of input parameters, what we do is we do a dimensional analysis, which is nothing but your Buckingham pi theorem is one of the tool where you do the dimensional analysis. Okay, and then you convert this equation into a non-dimensional numbers. So this, when you do the Buckingham theory, which you are not doing to, but I'll just show you. Once it is done, it is expressed in something like this. Okay, so this is your Reynolds number, this is your the discharge coefficient, the capacity coefficient, this is your head count. So whenever, and I mean the general practice in the dimensional analysis is express the output parameter of the parameter of desired interest in terms of the factors which it depends, and then convert that by applying a dimensional analysis technique, convert then into the non-dimensional numbers. That is, if pi1 is one dimensional numbers, it will be a function of pi2s, pi3s, and so on. So all these are non-dimensional numbers. The importance of this is once you convert into non-dimensional numbers, the major point or the concept in why we do this is that these non-dimensional numbers don't change. Non-dimensional numbers don't change, do not change with change in operating response, with change in operating response or scaling. And that's why, like when you're, for example, when you're testing a aeroplane or when you design an aeroplane from concept design, so you develop a prototype and you measure the performance in that, and then how do you relate this prototype performance to your actual model performance is by your scaling laws, and these non-dimensional numbers don't change during scaling. So that is one important concept in, that's why we do this dimensional analysis. So now what I mean is this, the CH, CQ and RE will be same. The CH for the model 1 will be equal to the CH for the model 2 if you have done scaling or if you have changed in operating response. Your CQ will be same for model 1 and model 2. Model 2 can be prototype. Your Reynolds number will be same. So that's an important thing. So another important parameter which we express most of the time is your specific speed, pump specific heat. That is again one of the dimensional, another non-dimensional number which is again a functional of CQ and CH. Okay, so combining the CQ and CH, the head coefficient and the capacity coefficient, if I combine, I get the specific speed, and that formula comes out to be something like this: n root q by h 3 power 4. So the meaning, I mean, you can say, okay, specific heat is the speed of the pump with which gives takes one volume flow rate, which takes unit volume flow rate and delivers unit head. Well, that and all is based on this formula, but remember that it is another non-dimensional number and it doesn't change with scaling or change in the operating hour. So if you are given with one pump and speed is changed and asked what is the head, then you can just say that the specific speed remains constant. So now I list out all the pump scaling laws, so that all the problems, all your scaling problems or your change in operating response, you can use these three, combine these three and solve everything. So n root q by h 3 power 4 is going to be same between model and prototype. Prototype is your actual, model is scaled, okay, or you can say between model 1 and model 2. So this is one of the pump scaling law. The other is h by n square d square between the model and the prototype. So I'm just writing prototype. And the other, so this is first scaling law, the second scaling law, third scaling law is power q and h, power delivered, the power required actually here. So q h between the prototype. So this is third scaling law. So these three are enough. Like if say if I build a 1/10 of the scale model of the centrifugal pump, 1/10 model of the centrifugal pump, and I know the head it is delivering, so I can just find out the head. So all these are your mapping you can use, or even two things here as scaling as well as to know to to know the change, to know the operating response, to know the change in one of the parameter when the operating response when one parameter is changed. So these equations will help you in that way. So that is one thing. So let's do a problem on the scaling laws of the pump. So what is given is, let's do a problem. A centrifugal pump has an efficiency 80%. The specifications are discharge is 70 meter cube per hour, head is 7 meters, speed is 1450 rpm. And now what he says is that if the speed is increased to 1750 rpm, calculate discharge, head developed, discharge and the head developed. Okay, so how do I calculate discharge? My scaling laws. So let's write down my scaling laws and then see whether in which one of the law it fits in. So my scaling laws are like this for the pump. N root q by h 3 power 4 is constant. Let me first write down and then we'll see which one fits in. The other is h by n square d square m is constant, and the other one is between power is constant, or you can just write constant. Okay, so what is asked is if the speed is increased. So here what they are doing is they are increasing the speed and the discharge will change, obviously the head also will change. So I can use this, right? So I need to eliminate either these two if I combine. So I can write n root q by h I can write in terms of this. So h can be written as some constant n square d square whole power 3 by 4. It has to be constant, right? So what I've given is I want to convert everything in either I mean speed and one parameter, one varying parameter. So here you have h, as speed is changing, q and h will also change. So here I have h and speed and diameter. So I'll just express h as n square d square, some constant n square d square, that here. So finally, what does this become? Root q, n square is n 3 by 2. Diameter is constant because this is just changing the operating, same centrifugal form, so diameter is constant. So I can write in this way, and this I can write root q by, the diameter is not changing, so I've just removed the diameter, and this can be written as root, yeah, so this can be written as n 3 by 2 minus 1, that is 1 by half, equal to constant. So basically this gives that q by n is constant if I square it. So n1 by q1 is n2 by q2. I want the discharge, so q2 is q1 n2 by n1. Okay, so q1 is 70, initial discharge, final speed is 1750, and this is 1450. So this comes out to be, 84.48 meter cube per hour. So the basic technique is you have used these two. I mean, the individual each is not sufficient, you have to combine here, because so best thing is to remember these three, and then based on the problem you have to combine. Now head and speed is asked, so head and speed I can straight away use the second one. So h1 by n1 square, diameters are not changing unless it is scaling, diameters will not change. So I want h2 is n2 square by n1 square into h1. n2 is 1750, n1 is 1450 whole square into h1 7. So this value comes out to be 10.196 meters. So if I change the speed to 1750 rpm, the discharge will change by this much amount, head will change by this much. So these scaling laws, three scaling laws, are very important. You can apply to any problem, and most of the gate questions come from centrifugal pump is either from the velocity triangle or from these pumping laws, pumping scaling laws. Thank you.